Let's go for lab 11, task 1. Use tornadoes data and use your statistical expertise to answer the questions. Is it reasonable to claim that the average number of tornadoes in April and August are different? We need to check the average number of tornadoes in April versus August, and are we sure? And we need to see whether they are different. Okay, whether those averages are different. That means this is the case of two-sided t-test. Okay. Then we would like to find the p-value. Let me open the tornadoes data, April and August. So this is April and this is August. Control C, come up with new worksheet, paste it. So two-tail test is equals t-test array 1. Array 1 is A2 up to A46, comma, second array is B2 up to B46, comma, the tail is two-tail test and 3 is the p-value. Okay, thus we get 8.17505 e to the power -06, which is a very small number, and let's try to see if there is this one. So this is the correct one, so B is the choice. Then statistical interpretation, the p-value is very small, so we would go for either A or C, since this and this cannot be the answer. Let's go for A. Since p-value is very small, we are confident that the tornadoes in April will influence the tornadoes in August. Since we are considering two-sided t-test, so influence, this keyword means regression, so we can't have A as our answer. So let's go for C. Since p-value is very small, we are confident that the average numbers of tornadoes are different. That's good, so this would be the correct answer. Since we in two-sided t-test, we are looking for the significance of difference between two averages. Okay, thus we can conclude that yes, I am confident that the above assertion is reasonable due to the fact that the p-value is very small. Task 2. Use the tornadoes data and your statistical expertise to answer the questions. Is it reasonable to claim that years with more observed tornadoes are the years with more tornadoes death? So it is saying that more tornadoes causes more deaths. So one variable, okay, more observed tornadoes will cause more deaths. So that means one influences another. So that's the case of regression. All right. Now let us again go to the same work, same data, tornadoes, and here we are trying to look at more observed tornadoes, the year with more tornado death. Let's select this one, the total tornadoes and total death. Okay, so we will be selecting these two columns. Control C and come up with a new worksheet and Control V. So we are comparing between these two, and we are saying that we are trying to claim that more tornadoes results in more death. So this will influence this one. That means this is variable X and this is variable Y. So let's go to regression, data analysis, regression, input Y range. Y range is simply total deaths. Okay, and X range is, and click on levels and click on OK. So we get the regression table, and the p-value is clearly 0.349. okay, p-value is 0.349, which is very large. Now statistical interpretation, we should be going towards this one, okay, or this one, since the p-value is not small. Okay, let's read B. Since p-value is not small, we cannot claim that the number of tornadoes will influence the tornado's death. So this is correct interpretation. So that's it. Now conclusion, since the p-value is very large, we cannot claim the above assertion is reasonable. So that's all. In task 3 also, use the tornadoes data and your statistical expertise to answer the question, is it reasonable to claim that on average there are more than 45 tornado related deaths in the month of April per year. Okay, so in this case we should compare the average tornado death in month of April for each year with a fixed number 45. So that's why we go for confidence interval. Yeah, let's again go for the same data. Tornadoes related death in April means we choose this column, Control C, and go for new worksheet, Control V. Let me remove these empty spaces. For confidence interval, the first one that we should do is find out the average. The average is 27.35. Okay, so average is 27.35. Now standard deviation equals STDEV from A2 up to A46, bracket close. 60.62 is our standard deviation, and then margin of error is given by equals confidence dot T. Alpha is 0.05, that's 95% confidence interval. Standard deviation is 60.62708, comma, total number of data points is 56 is the total data point, but we need to exclude the header, so that's why it is 45. So 18.21 is the margin of error. Now let's go for confidence interval. The left endpoint is equals average minus margin of error, that's 9.14, and the right endpoint is average plus 18.21, that's 45.56. Okay, now here you can see that what is the p-value or margin of error? We don't have 1.8, so none of this is the correct one. Now let's go for correct statistical interpretation. Here it says, is it reasonable to claim that on average there are more than 45 tornadoes related death? Now 45, that number lies in this interval. Okay, so we can't say that all the tornadoes related death are less than 45. Let's read this one. Since confidence interval does not include 45. No, that's not the correct answer. P-value, no, we are not dealing with p-value in this case. Since confidence interval includes 45, we are confident that the number of tornado related death is below 45. The first part is correct, but second part is not correct. Okay, sum of the tornado related death is above 45, since we have 45.56 also. Okay, so that's why we go for none of this. Thus we cannot claim that above claim is reasonable by 95% confidence. Okay. Task 4. Your insurance company has converged for 3 types of cars. The annual cost for each type of cars can be modeled using Gaussian normal distribution. The following parameters: car 1 type, mean 520, standard deviation 110. Car 2 720 mean, 170 standard deviation. Car type 3 470 mean and standard deviation is 80. Use random number generator and simulate 1000 long columns for each of the 3 cases. Example: car type 1, number of variables 1, number of random numbers 1000, distribution normal, mean 520 and standard deviation 110. Leave the random seed empty. Let's go to data analysis. This is random number generation. Click on OK. The number of variables is 1 for the car type 1. Random numbers, let's suppose this is 1000. Okay, and this is normal distribution. Mean is 520 and standard deviation is 110. Random seed, keep it empty. Click on OK. We get this data. Alright, now similarly for car type 2, go to data analysis again, random number generation, click on OK. Everything is fine. 1000 normal and mean is 720 and standard deviation is 170. Click on OK. So we get another data. Similarly, let's go to data analysis, and for the third car also we do the similar kind of thing. The mean is different, which is 470, and standard deviation is just 80. So click on OK. Alright, so we got these three things differently. Okay, in worksheet number 2 we have car type 1, worksheet 3 second type of car, and sheet 4 third type of car. Here it says that use either sorting to construct the appropriate histogram or rule of thumb to answer the question. Okay, what is the approximate probability that car type 2 has annual cost less than 550? Car type 2. Car type 2 is in worksheet number 3. Let me sort and filter the data. Okay, let me sort the data. So sort from smallest to largest. So the smallest is 153, and the largest, just go for control down arrow key, largest is 1333. So let me start the bin from 250 and increase by 150. Okay, so that's 400. So these are the bins for car number 2. Then go to data analysis, histogram, click on OK. Input range is from A1 A1000, and bin range is B1 up to B9. Okay, click on OK. So let me select this and insert and recommended charts, so the first one, and click on OK. Thus we get a nice bell-shaped curve. Here it says, what is the approximate probability that car type 2 has annual cost less than 550? So less than 550 means we need to go up to this one. Okay, so 3 plus 27 plus 140. 3 plus 27 plus 140 divided by 1000. Okay, 1000 items, so that's 0.17. Okay, so that's 17%. Between 1 and 3%, no, it's greater than 3%, but between 27 and 39, no, it's less than 27. 55 to 70, no, none of this. Let's go for this. Which of the three types of car is least likely to cost more than $700? I have come up with bins for car of type 1. Okay, and that's 250 up to 1000. Okay, we have already done this one, so let me do this again. So go to data analysis and histogram, click on OK. A1 up to A1000, that's fine, and for B1 up to B6. Okay, so that's good, click on OK. Then here in worksheet number 9 we get this one. So above 700, okay, up to 700 we have this much data. Beyond 700 or above 700 we have 49 plus 2, that's 51. So this is type 1 car, right? So this would be equals 51 divided by 1000. So that's 0.051 is the probability car of type 2. Okay, also go to data analysis, histogram, click on OK. A1 to A1000, that's fine, and bin range is B1 up to B9. Click on OK. Then in worksheet number 10 we get this table. So this is type 2, and this one is so the total probability is beyond 700 we have 312 plus 162 plus 40 plus 5 plus 1, that's 46. 520 divided by 100,000 is 0.52. So 0.52 is the probability type 2 cars will spend more than $700. Now let's go for type 3 car. Here the least amount is 210 and the highest amount is 717. So that's why I went for 300, 400, 500, 600, 700 and 800. Now again go to data analysis, histogram, click on OK. Input range A1 up to A1000, B1 up to B6. Okay, okay, B1 up to B6. Alright, so then click on OK. Thus we get this one. So this is type 3, and beyond 700 we have just 3, that is equals 3 divided by 1000. Now if you compare these three things, worksheet number 9, 0.051, 0.52, 0.03, so type 3 car is least likely to spend more than $700 for maintenance per year. So type 3 car. Okay. For which type of three types, for which of the three types we have the highest probability that it will cost between 400 and 500. 400 and 500, let us redesign the bins. Okay. For type 3 car we are good. For type 2 car, let's go for type 2 car and readjust the bins. Okay, so this is let us go for 200. This would be 200, 200, 300. Okay, this is for type 2 car. 200 up to 1400 is the number of bins. Go to data analysis, histogram, click on OK. A1 up to 8000, that's fine, and B1 up to B13. Click on OK. So we have all of these things. Then this is type 2 car, right? Type 2 car. Okay. Right. And for type 1 car also we do the similar kind of thing. Let us readjust the bins. Okay, for type 1 car we have adjusted the bins. Go to data analysis, histogram, click on OK. A1 up to 8000, that's good. For bins, B1 up to B9, and click on OK. Thus this is type 1 car. Okay, let's find out the probability for this one, 400 up to 500. Okay, that the cost range, so that would be just simply 273. Okay, so equals 273 divided by 1000. For type 1 car, 0.273, that's fine. For type 2 car it is 400 to 500, that means go for 69. So equals 69 divided by 1000, 0.069. And for worksheet number 11, this is equals to 400 to 500, that's 445 divided by 1000, equals to 0.445. Type 3 car has probability 0.445, type 2 car has 0.069, and type 1 car has 0.2373. So type 3 car has the highest probability, okay, that it will cost between $400 to $500. So that's type 3. Tutorial, we have already done this tutorial in lecture number 26, so please go through it. Let's go for task 5. Task 5. Using the previous tutorial, address the following. Imagine an experiment where 3 dice are tossed, 3 dice are rolled, and the number on each die is recorded on the die 1, die 2, die 3. Answer the following questions about the sum of the 3 numbers recorded, die 1, die plus die 2 plus die 3. Hint: simulate the experiment 1000 times. Okay. First, let me draw the tables. Okay, outcomes and probability. Alright, so outcome is 1, 2, 3, 4, 5, 6. Okay, the probability is equal 1 over 6. That's fine. Now drag it down. Then go for random number generation, data analysis, click on OK. Here we want discrete. Okay, value and probability input range is A2 up to B7. Okay, that's fine. We need 3 die. Okay, we need 3 die, so that's why we have we want 3 variables. Okay, that means we are rolling 3 dice and we are rolling them 1000 times. and the value and probability of input range is A2 up to B7. Alright, and click on OK. We should be getting die 1, die 2, die 3, okay, for the first trial, second trial, and so on. Now column D will be the sum of those three, okay, sum, okay, so that's sum 14, and this now after hover at the right bottom corner, and after you see this kind of black plus sign, then you double click thousandth toss or thousandths roll. You can see this is sum A1000 to C1000. Okay, now after we have done that, so then here it says that, okay, we have already done this one, we have also done this one, we have summed up those things, and finally create the histogram based on this new column. Use bins 3, 4, 5 up to 18. Bins are 3, 4, 5, 10. So these are the bins 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Then go to data analysis, histogram, click on OK. So here this is D1 up to D1000. So let us go for D1 up to D1000, and E for this one bin range, you go for E1 up to E16, okay, and click on OK. Thus this is our data, this is our table. So here insert recommended charts and click on this one and click on OK. So that's our histogram. Alright, now it says what is the approximate probability that die 1 plus die 2 plus die 3 equals to 10. So for 10 we have 111, okay, so that's 111 divided by 1000, okay, since there were 1000 rolls, so 0.111. The probability is approximately 10%, okay. 0.11 means it's actually 11.1%, so approximately 10%. That's fine. What is the approximate probability that die 1 plus die 2 plus die 3 is greater than 10? So greater than 10 means we all go for this one, okay. So let us add all of this, sum from 11 up to 18, okay, yeah, divided by 1000 equals 0.522, okay, 0.522. that's our probability. 0.522 means it's 52%, 52.2%, so that's approximately 50%. What is the approximate probability that die 1 plus die 2 is 9, greater than 9? So for this one, die 1 plus die 2 is greater than 9. Let's come up with the cell. Let us copy these two cells and paste it somewhere here, okay, Control V. That's die 1 plus die 2, and now so the here equals sum, and this is from I1 up to J1, okay, so that's the sum. So that's all. Now double click here, then everything gets populated up to 1000th row. And now let us go for the bins. The bins are the same, okay, E1 up to E. Then go to data analysis, histogram, click on OK. This would be K1 up to K1000, K1 up to K1000, and number of the bin range is E1 up to E16, E1 up to E16. That's fine. So click on OK. Thus we get a different thing, okay, different number. So D1 plus D2 greater than 9, right? Okay, that's what we want. So the probability is equal to sum from greater than 9 means from 10 up to 18, okay, 10 up to 18 divided by 1000, 0.186, that is 18%, 18.6%. So approximately 18% is nearer to 15% than 25%. So let's go for this one. Okay, so that's all. Now let us go for task 6. Open hurricane data. Is it reasonable to assume that average hurricane deaths in 1960 are not different from those of 1970s? Given the data, your job is to check if this assertion is indeed reasonable or not. Hint, read lecture 24. At the end of lecture 24, okay, you can see that rules of thumbs for null hypothesis. The population's averages are equal for two-sided test. Slope of regression line is equal for regression test. Okay. Then then what would be the null hypothesis? Okay, so here, is it reasonable to assume that average hurricane death in 1960s are not different from those in 1970s? So we are comparing the average hurricane death in 1960 versus 1970s. So that means this is the case of two-tail test. For two-tail test, we go for population averages are equal. Okay, that is the null hypothesis. So that means we go for this one. Okay. The p-value is 0.58. What can statistically be concluded? Okay, we cannot reject the null hypothesis since the p-value is way higher. Okay, 0.58. Write a one-line additional comment. We cannot conclude that the data related to two decades are related. No, the relation means regression. We are not talking about that. We are confident that hurricane deaths for 60s and 70s are similar. No, we can't say that since p-value is greater, so we can't say that. We cannot conclude that the hurricane deaths for 60s and 70s are different. So this would be the correct one. So that's all.